Hello everyone, welcome to Dakshana e-classroom program. So in last few lectures we were talking about the measurement of activity, measurement of radioactivity. We saw a few terms like the reactivity, activity is the decay rate at which in radioactive nuclei convert to another nuclei, and we saw a few terms like average life, half-life, what should be the meaning of them, the formula, you should remember those. We further saw like sometime a radioactive nuclei simultaneously break down, is it, or decay into two nuclei, so we call that as like a parallel decay, and sometime a radioactive nuclei like A decaying to some B and B also further decay to some C, we call that successive disintegration, successive decay. So in both cases, if anything is asked about the number of nuclei of any element or any atom present at any time, we get the expression, and we also saw how we calculate that. In parallel decay, actually the probability, like this is A, it's probability decaying into B and C, so there is different probability of decaying A to B or A to C, and if their decay constants are lambda 1 and lambda 2, we get the effective or average decay for this decay of A is given by lambda 1 plus lambda 2. We calculated the expression for B and C, and so that similarly when A decaying to B and B decaying to C, this is lambda 1 lambda 2, this we call successive disintegration. So in such cases, like how we can find the value of or number of elements, number of nuclei of B, C or A at any time, we saw that too. So these things are important from your problem point of view. Many times questions are asked based on these things, like we will discuss. I have written one question, we will discuss more questions based on that how like different types of problems can be formed on that, on these topics, and how we can solve. So let's continue without delay. Let me first solve the application of these things here with this example, and then we will continue with the more topics. Okay, so let me read the problem here first. Try to understand the question, what it is exactly saying, then we will think about its answer. So here, a factory produces radioactive substance A at constant rate R. So here this initial production house is factory which is producing A at constant rate R nuclei per second, is it like that, with decay constant lambda to form a stable substance B. So A is further decaying to B, and with the decay constant lambda, this is rate of production of A, and this is the decay constant for A to produce stable nuclei or stable substance B. This is what happening here actually, and which decay with constant lambda to form stable nuclei, stable substance B. Now we are asked to find the number of nuclei of A at any time, number of nuclei of B at any time, assuming production of A start at t is equal to 0. So I can write at t equal to 0, number of nuclei of A is also 0 and B is also 0, means initially there is no number of nuclei of A is present and also B is also not present. And assuming that production of A start at t is equal, this means that. Also find the maximum number of nuclei of A present at any time during its formation. So you can see it's also one of the application of successive disintegration, successive decay. अब देखते हैं like how we can solve this problem. Okay, it's not difficult, it's basic thing. We need to just go with the approach that we have seen just now in the last lecture. Okay, you should remember the formula, you should know the approach. So now I can write here, let at any time t number of nuclei of A formed, or I will write present, is it, is n. I am assuming that at time t A has number of nuclei, so I will write at time t, let's say it has some n, and I will write its sum, let's say nb, or let me write it na and nb. Is it? So at time t A has Na and B has also Nb. All right. Now see, A is a radioactive nuclei. It is forming at the rate of R, is it? A is produced at the rate of R, means I can write d and A by dt. Production rate, produced rate is R. Simultaneously it is also decaying to B, is it? So rate of decay of A to B, this I can write d and A by dt. This rate is decay. This is equal to what? Lambda times Na. It will be negative because it's decreasing actually. The effective rate of change, or you can write production of rate of change or rate of production of nuclei A, this can be written as d and A by dt. So this is the rate of production minus rate of decaying, and that comes out to be R minus lambda times Na. Right? This is, now we can further simplify it, we can integrate it, and let's get the number of nuclei A present at any time t. So I hope everything is clear up to this step and there should not be any confusion to anyone. This is the actual thing. The problem given in the question, actually we have just written it symbolically, that what is actually happening in the factory. From like scratch or from raw material, A is being produced. A is further and this produced at constant rate R. This is decaying to stable nuclei B. So finally B is also being produced. T is equal to 0. There is no element of A and B present, no number of non-nuclei of A and B present. Let me say it at time t, Na and Nb are the number of nuclei of A and B. So I write produced rate, decay rate, so effective rate of change, produced minus decay. So now I can simplify it further. This implies d and A divided by R minus lambda and A equal to what? Dt. We can integrate it on both sides. So here 0 to t, and at t is equal to 0, what is Na? It's 0, and t time, let me write it Na. Now if we integrate it, it will be ln R minus lambda Na divided by minus of lambda. So integration comes out to be minus 1 by lambda ln R minus lambda Na equal to t. And if I substitute the limit 0 to t and here 0 to Na, then I will get, this implies minus 1 by lambda, this is ln R minus lambda Na divided by R, if I am substituting 0, equal to t. I can multiply it that side and it's ln R minus lambda Na divided by R equal to minus lambda t. This can be further R minus lambda Na equal divided by R equal to e raised to power minus lambda t. R can be multiplied here and this I am rearranging. Finally I am getting Na is equal to R by lambda 1 minus e raised to power minus lambda t. So here you can see easily, very easily, with simple integration process, we got the number of nuclei of A present at any time t. We can express that in this form. Na is given by R divided by lambda bracket 1 minus e raised to power minus of lambda into t. So here up to here we got just the number of nuclei of A. Alright, so this is part, basically I will write part A. This is done. Next it is asking also number of nuclei of B at any time t. So for that let me erase first this part. So there are two ways actually we can write or about B. Is it 1B is rate of formation of B is equal to rate of decaying of A, and we will integrate that, we can get it. or another way. So let me first tell you the easiest way. So in this case, let's say this is method 1. So here, see, initially t is equal to 0, number of nuclei 0, number of nuclei 0. A is being formed at constant rates at time t, is it? At time t, how many number of nuclei of A produced, or at instead of by time t, number of nuclei of A produced total. This can be written as R into T, right? So total number of nuclei produced, ultimately only A is produced. From A some B is produced, is it? So total number of nuclei of A produced by the time t can be written as RT, right? And I can write at time t, RT will be equal to number of nuclei of A plus number of nuclei of B. Do you agree with this? Because try to understand, from some raw material, we don't know what is that, from that A is first produced and it's being produced at constant rate. So if A is not decaying further, then at time t, number of nuclei of A present or should be present will be equal to R into T. But because A has decayed to some stable nuclei B, so means this number of produced number of nuclei of A might have reduced with some amount, is it? And those reduced number of nuclei will be converted into B. So I can write at any moment of time number of nuclei of A plus number of nuclei of B must be equal to total number of nuclei of A produced from 0 to T time. So I can get this expression. Na we already have, NB from here we can write this, NB is coming out to be RT minus of Na, and this comes out to be, I can substitute this value, RT minus R by lambda 1 minus e raised to power minus lambda t, and this is your answer, and this is the number of nuclei of B at any time t, right? Another method, this you can write that dNA by dt, is it? This is decay, that is equal to lambda into Na. This should be equal to what? dNB by dt, at which NB is being produced, right? Na I already got, substitute Na and then integrate this process, you will get exactly same result. So this is your another method. I am not going to solve it to the final step, you can go for it and try it, you will get exactly same answer. So this is just one of the application of the successive decay, or the part that we discussed in the last lecture. Okay, so I hope you are clear with the part here. Good problems are formed, and if you understand the concept, go it step by step. I don't think you will be stuck anywhere. Things are not that much difficult also, is it? At least for these problems, yeah, I agree that there may be some like high level questions there, you need to think more. For that, first our like approach is to get it familiar, get it clear with the concept. That should be your target right now. Your target now should not be to deal with the high level of problem, it should be just to get familiar with the concept and its application. And for that, if you are just understanding that, then this is good enough. Try more problems. Let me solve few more cases so that you are like feeling better, is it? Let me first erase this part. Okay, wait, actually I missed the one last part in that question. Here it was asking like the maximum number of nuclei of A present at any time, is it? So maximum, so I calculated Na is equal to R divided by lambda 1 minus e raised to power minus lambda t. So this is the number of nuclei of A present at any time t, is it? We need to find its maximum value. What will be the maximum number of? So you can go with simple approach of maxima minima. So maximum number of nuclei of A present To calculate this, we can get first dNA by dt. This is r by lambda, differentiation of 1 0 minus differentiation e raised to power minus lambda t into minus of lambda equal to 0, and this implies minus lambda t equal to 0. This implies t is equal to infinity. So we understood the maximum number of A will be present at infinite time, is it? So maximum number of nuclei of A will be at t equal to infinite, or you can write after long time, right? This is, and then we can get it directly. So maximum number this you can write Na max simply r by lambda e raised to power 1 minus e raised to power minus lambda into t, that is equal to infinity. So this quantity becomes 0, so we are getting simply r by lambda. This is the maximum number of nuclei of A present at any time, and we also got the value of time at which it will be maximum, that is t is equal to infinity. So this I just missed it in the last question, so I hope this is clear. Just now we solved. Okay, let's see next application, next problem. So let me read the problem first. The mean lives of a radioactive substance are 1620 years and 405 years for alpha and beta emission respectively. Means mean life means average life. Average life for alpha emission is 1620 years for the radioactive substance, and lambda for beta is given by 405 years for same radioactive substance. Now we are asked to find out the time during which 3/4 of the sample will decay if it is decaying both by alpha and beta emission simultaneously. So the point is here, alpha and beta emission is happening simultaneously, right? So the thing is, now it's not simple decay, it's something different, and that is actually when emission are happening simultaneously, or emission is happening simultaneously. So let me write A is that radioactive substance, and this is decaying by alpha decay, so for that it's lambda alpha, and by beta decay then it's lambda beta, to let's say some C, some B, or some C radioactive, B or C some substances. So A is the radioactive substance, it is decaying to B and D. B and C I am writing it's like through alpha decay it's going to B, through beta it's going to C, and this emission, this decay is happening simultaneously. So we can just see directly it's a case of parallel decay. Parallel decay, right? So this is the case of parallel decay. Now it is asking by the time for which, like a time by which it will be 3/4 of the substance A will be decayed. So first thing is, here we are not supposed to bother about B and C, is it? We are still talking about A. So A simultaneously decaying with alpha and beta decay. Their mean lives means lambda are given, so I can write T half or half lives for, so T here I am directly writing T half is, this is for alpha can be written as 0.693 divided by lambda alpha. I can substitute the values, and similarly for T half for beta decay, this is 0.693 divided by lambda beta. I can write it directly T alpha, or this is T beta also, right? So now first I'm like effectively with what, or what is the mean life, or effect, what is the effective decay rate, decay constant for decaying A? So the average decay constant for A. So this we have already calculated. A average, A effective is given by lambda 1 plus lambda 2, and so lambda 1 we are here, actually this is lambda. All right, just 1 second, let me just check the part. Okay, so the effective basically average lambda or effective lambda or mean life for A decay can be written as this, and that comes out to be 1620 plus 405, and this is equal to 2025 years, right? So the effective half-life of A decaying simultaneously by alpha and beta emission, so then T half-life for A is coming out to be 0.693 divided by lambda effective or lambda average. Next part, see, now it is asking, the question it is saying, find the time during which 3/4 of the substance will decay, is it? So 3/4 of substance will decay means 1/4 of A is left. 3/4 has decayed means 1/4 has left, and 1/4 left means how much duration? That we can directly straightforward, because we know this n is equal to n naught divided by 2 power n, so this is n naught by 4. This implies n equal to 2 half-lives. So the duration by which 3/4 is decayed and 1/4 is left, that is equal to 2 half-lives, and we know already half-life is equal to this. So the total duration by which 3/4 of the substance will be decayed, so the time by which 3/4 of the substance will decay, this is equal to how much? 2 into T half-lives, and that comes out with 2 into T half is how much? This is 0.693 divided by lambda effective. Is it clear? And that comes out to be, we can just simply calculate it. Let me just check the calculation. We have everything all right. This is good. Okay, so now I can substitute the values here, and this comes out to be just wait. Okay, actually there is one mistake I did, sorry for that, and listen it carefully. You should not get confused with anything. I just did one small mistake. The point is, here it's saying the mean life of radioactive substance for alpha decay and beta decay this, and I took that mean life simply equal to lambda. Actually the formula is mean life or average life, this is equal to 1 by lambda. So I should write, actually this is equal to 1 by lambda alpha, not simply lambda. Similarly this should be 1 by lambda beta, is this. So lambda alpha is 1 by 1620 years, lambda beta is 1 by 405 years. So one thing is this is all good, all okay. Here relation this all we can write. Next change will be here, because now lambda 1 lambda 2, it will be 1 by 1620 plus 1 by 405, and after solving this we are getting, it's basically taking LCM, so it's in numerator 2025 divided by 405 into 1620, and that comes out to be 1 by, this simply gets cancelled 5 times, and this 324. So this is your lambda mean year inverse. Okay, lambda average, lambda effective we got. Now the effective half-life, we can write lambda effective here or lambda average here. It's means same, lambda effective. Okay, so we got this, and now 3/4 of the substance will decay by means 1/4 of the A is left. So how much time it will take to, like, for a radioactive substance to decay by 3/4 or to remain by 1/4, and that is equal to 2 times of half-life. And this time we can write 2 into T half-life, and T half-life is given by this. We can substitute the values, and now lambda effective, so it's 2 into 0.693. Lambda effective is what? 1 by, like here it's coming 1 by lambda effective. Lambda effective is 1 by 324 year inverse. So 1 by lambda effective will be just inverse of this. So we can substitute 324 year, and after solving this we can simply multiply. It's coming out to be 449 year. So this is the time by which 3/4 of a substance will decay and 1/4 will be left. Just small correction, you should not get confused. There is no problem, remaining everything is correct. So now you should change, check this, you should keep that in mind. Remaining thing like mean life, so we should write it 1 by lambda instead of lambda, that I wrote by mistake. And this is now, like, so we got lambda 1, lambda 2, and we know actually T half relations. If you require, we can get it this way. And the average decay constant or effective decay constant can be expressed this way. This we know already in the parallel decay. The effective or average decay for substance A is given by lambda effective is equal to lambda 1 plus lambda 2. By using simply lambda 1, lambda 2, we are getting the lambda average or effective value is this. So now for A, I can write A is decaying with T half-life is 0.693 divided by lambda effective. Next point is simply it is saying 3/4 of A has decayed or should be decayed. That implies 1/4 of A is left. 1/4 of A is left, we can get it that how much time it will take. Whenever it comes like 1/4, 1/8, 1/16, so these things you can connect directly with the T half. When it is like saying 10% is left, 20% is decayed, in such cases you need to do with the calculation part, that is n is equal to n naught e raised to power minus of lambda t. So there you write n naught, is it n is equal to n by 20, 30, 40, 50, 25, something like that. There you can go. When it is like 1/4, 1/8, 1 second, so that means you can directly connect it with T half-life. So this implies the duration by which 3/4 is decayed means like 2 half-life, and we can get the value of 2 half-life, and solving we are getting this. So this is the final answer of this problem. So this is one of the application of parallel decay. So I hope you are clear with this two part, that is parallel decay and successive disintegration. Try more problems based on it, and let's continue with the next part. Okay, so the next topic we are going to talk about is radioactive dating and aging. This is one of the application of radioactivity. Actually, you might have definitely heard many news about that like some thousand and lakhs of year old something is found, some skeleton is found, some fossils are found for some animals like which were existing on the planet, on the earth long times back. So like we even calculate their ages, the time, like 1 lakh year old, 2 lakh year old, and some thousands of years old. So have you ever wondered that how we are able to predict the age of those things, that how we can predict that something was existing there thousands and lakhs of years ago? And the point is that yes, those things can be understood, can be answered with the help of radioactive dating and aging. So now we are going to see those points, those things, that how exactly we can find the age of some rock, the age of, or like how old it is actually, some rock, some skeleton, or something like that. Okay, so that is basically we studying in radioactive dating. So here there are many ways, but we are going to study only that is two. So we have like that is carbon dating and uranium dating, right? So what is that? So dating means finding age, it is means finding the age of very old rock, skeleton, or any which was live on earth long time back. Is it? So we have actually two methods for finding their age. One is called carbon dating. Another is uranium dating. So now we will see that what is the difference between these two and how we can use and when we should use which one. That will be also clear. So the carbon here we use, let me first talk about this first one, that is carbon dating. So carbon has actually three isotopes. So here carbon has three isotopes. Isotopes are means like us. What is the isotope? Isotopes means like elements having same atomic numbers or same number of protons but different mass number. Those elements are called as isotope. So like carbon, three isotope, then it has like atomic number is always 6 or number of protons, so it has like 6, 12, carbon 6, 13 and carbon 6, 14. Out of these available three carbon isotopes, this is radioactive element or radioactive carbon isotope. Carbon. Okay. And one more thing actually, like how now we are going to understand is that how we can use this carbon dating, how we can with the help of this, how exactly it works, and how with the help of this we can find the age of something like which was earlier existing, right? So to understand that, here I am saying one point that, so there are two things actually. One is living organism, maybe plant, animals, anything like that. Another is dead one, is it? The like a human body or all the animals, they are mostly made of what? Carbon. Like the content of carbon in anything like which is existing on the earth, it's like too much, is it? In that too, if I talk about the carbon 12 and carbon 14, is it, ratio, if we are taking any small amount of sample from anything, any plant, any body, and measuring the number of carbon 12 elements and number of carbon 14 elements, then the ratio of these number is fixed in living organism, is it? I will tell you how it is also fixed, how it is maintained constant. So the ratio of number of carbon C12 and C14 atoms is constant in all living beings, whether it's plant, animal, anything like that. If it is alive, it is living, then this ratio always remains constant, and this ratio is actually C12 versus C14. It's actually 8.3 into 10 to the power 11 versus 1. We take it roughly 10 to the power 12 is to 1. Means in every 10 to the power 12 atom of carbon 12, one carbon of like one atom of carbon 14 will be available, is it? So in 10 to the power 12 atom of C12, one atom of C14 will be present. Remember, this ratio is in living organism, living plants, living animals. Once it is dead, then this ratio gets started disturbing. So let me first tell you that how the ratio is maintained constant in the living beings, is it? So for that, everyone, like we, all the living beings, they take or intake carbon in some forms, and in the upper atmosphere, is it upper atmosphere, there is nitrogen, oxygen, all those things are available. So there is one nitrogen 714. When some cosmic radiations or cosmic rays are falling on it, this convert this carbon like nitrogen 14 to carbon 614. So here what is happening? One proton is getting converted into neutron. So that's why number of nucleons, number of mass number is remaining constant, but proton is changing. And here you can see the nitrogen is getting converted into carbon 14 with the release of one beta positive plus antineutrino. Yes, this is happening in the upper atmosphere where cosmic radiations are falling from the sun, and nitrogen is getting converted into carbon 14 element. This carbon 14 element 614 combined with oxygen and form CO2. Right, and this CO2, because it's heavy, so it comes down on the earth near the atmosphere, near the ground surface. And when we are like taking carbon 14, CO2, then this is going into the body of all the living organism. So we take, or I will write, all the living organism take CO2 14 from atmosphere and as this is like if we are continuously intaking, then what will happen? Like ideally the number of carbon 14 elements in our body or in the body of living organism and plant must increase, but because this carbon 14 is also a radioactive substance, so it keep on continuously decaying simultaneously, right? So we are like all the living organism take carbon 14 CO2 from the atmosphere, and simultaneously it also decay at some rate with half-life equal to 5730 years. So in this way, like when plant, animals and organism, they are alive, they are taking carbon 14 CO2 from the atmosphere, and so intake is there, and because it's radioactive elements, simultaneously it will be also decaying, and in that process all these things happen always such that this ratio of carbon 14 and carbon 12 is maintained constant. Is it? So this is the thing happening in the living beings, living organism. But what happens once the plant and animals are dead, right? When they are dead, then you can imagine easily that there will not be any intake of carbon 14 in the body, or carbon 14 intake will stop, right? But because carbon 14 element present in the body and they are radioactive, so they can't stay there. What will happen? It will start decaying, it will start converting to some other stable elements. So in that process, in the dead animals or dead plants, so by this time you must be clear that how carbon 14, carbon 14 versus carbon 12 ratio or number of elements, number of atoms is maintained constant in the living beings. That should be clear to you up to now. Next point I am trying to say is that when plant or animals are dead, once they are dying, in that case no intake of carbon 14 6 CO2 is there, but whatever the carbon 14 element available in their bodies, they keep on continuously decaying, and the available C14 6 carbon atom keep on decaying as it is radioactive. So what happened actually, once the things are dead, plants and animals are died, they are not like living anymore, in that case this ratio started disturbing, is it? So keep on decaying so that the ratio of C14 and C12 get disturbed. And now this principle is used. So now we know actually if we are taking some sample, is it? One sample, let's say we are trying to find the age of any like plant. So we will take one is the like plant sample or sample from the that dead or like fossil of the plant. We will take, let's say, some 10 gram of sample, and we will take similar 10 gram sample from the new living plant, is it? We will calculate the number of carbon 14 elements present in the old one and present in the new one, is it? So that ratio ultimately we will get carbon 14 in the like living being and carbon 14 number in the dead elements or dead plant or dead basically body. Now we, with the help of those, we can compare, we can get the actually like age. So let me tell you. So I hope by this time you should be clear that how carbon 14 carbon 12 ratio is maintained constant in living being, how it get disturbed when the plant or animals are not living anymore. So now let consider two sample, one from living and another from dead of same plant or animal. So now we take two samples. So let's say I am taking 10 grams of this, like I am writing new and old sample, and I took basically new, I took let's say 10 gram sample, and old also I take 10 gram sample. As this 10 gram sample, it would be like made of mostly like carbon parts, so I can get the total number of carbon, and in this one also we will get, actually once we have total number of carbon, we can get the number of carbon 14 atoms by using this ratio, because this is new living one, so this ratio will be constant. So I can ultimately get the number of C14 atoms is calculated. So let's say this is the N, new is the N is the number of carbon 14 atoms present in 10 gram sample of new newly taken sample, is it, from the living being. And similarly this old sample, same 10 gram, and I am calculating the number of carbon 14 elements or atoms present in this. So let's say this is what, N naught. So now what do you think, like 10 gram sample, 10 gram sample, which one should be higher, right? Remember that. Here what is this? This ratio is for 12 and 14, it's this maintained constant that I just erased, 10 is for 12 is to 1. In old one, what is happening when it is new, it is living, then the ratio of 12 versus 14, it's 10 is for 12 versus 1, and that's constant. But in this one there is no intake, so carbon 14 will keep on decaying. So can you just imagine, now this one will decrease, understanding? And if we have some like let me erase this part. Next we know actually the number of element, number of radioactive element at as function of time, the relation we know already. So here first thing is I can write N new should be higher than N old, right? And we know the relation here, n is equal to n. This n naught is for that formula we have used, minus of lambda t for any radioactive sample. So now if I write this expression in terms of these two, then I can write actually n, this is the, is it now left one, this is equal now in the old one, so initially these one number of carbon atoms e minus lambda into t. I can take it log on both sides, and this comes out to be ln n naught by n equal to, if I take ln this side, so it's minus of lambda into t, and this implies t is coming out to be 1 by lambda ln n divided by n naught. Remember here n means number of carbon 14 atoms present in 10 gram. You can take it 10 gram, 100 gram sample, whatever it is just one example I have considered here. It's not like necessary that always you should be taking the sample of 10 gram each only. That is not necessary. So here n is the number of carbon 14 element present in 10 gram sample of new, like newly taken sample or sample taken from living plants or animals. Here this old same 10 gram sample, and we are calculating the number of 14 carbon 14 element present in this, and that is this one n naught. Because they have decreased, some element, some atom has decayed, that's why I can definitely say this will be less than this. And the relation between these two, we can write it by simply relation for number of atoms, number of radioactive nuclei for a radioactive atom or normal radioactivity what we have seen, we can use that relation. So you know this relation. Now if I substitute these values here, then it comes out to be this, and like rearranging it, I am getting this. So now if you know this, you know that, then you can get the time, that how old, how much time it has taken to decay from here to there. And this t will be the age of that sample. So this t is the age of that sample. Lambda we can calculate because we have already here t half, this is coming out to be 5730 years. So once we have t half, lambda is equal to 0.693 divided by t half, or you can write it's ln 2 divided by t half. So this is your lambda, you can use it here. T is equal to lambda, if I substitute it, then it's t half divided by ln 2 multiplied by ln n divided by n naught. So by solving this, you can get the time that, and this will be the age of the sample you are interested in calculating. So this is the process, and we call it carbon dating. So we can use the carbon dating when the age is in some thousands of year old, 5,000, 10,000, 20,000, 50,000, something like that. Then it is always better and advisable to use carbon dating process. When the age is actually, let's say, in lakhs, is it lakhs of year old, in that situation, because here the half-life is very, like, if I compare it with the lakhs of million and billion of year, in that situation this half-life is small. So in 1 million years of old, if I go with this carbon dating, then by that time this number of carbon 14 elements left in that will be almost negligible and will not be like accurate to calculate. So that's why in such cases we can't go with this carbon dating method. We need something like another element which has even higher half-life, and that is basically, so you should be understanding now, when the age of something like which we are interested to calculate is in the millions and billions of years old, then carbon dating will not work. There you need to go with the uranium dating. So this is about carbon dating. Let me explain you next, that is uranium dating. Before that, let me solve you one problem based on its application. Okay, before that I need to mention one more point here. So we got T is equal to, this is T half divided by ln 2, multiply this in L and N divided by N naught. So the point is that sometimes it is actually difficult to calculate the actual number of carbon 14 atoms elements present in some sample. So instead of going for the actual calculation of number of carbon 14 elements, we can go with the activity of carbon 14 elements present in the sample, is it? So instead of calculating the number of carbon 14 atoms, because it's not easy, is it? We can find the A's even with activity. So activity means we can calculate activity in the old sample, activity in the new sample. So right, see, activity in the old sample, what we can write, A old will be equal to dN by dt, and this is equal to lambda times n in number of elements present in old sample. Similarly, activity for new sample, this you can write an is equal to dN by dt, and that is equal to lambda times nn. From here actually I can just simply divide and I get a naught divided by an. This is equal to what? This divided by that, lambda lambda gets cancelled, and this comes out to be n naught divided by n nu. So this you can write n by n naught is coming out to be an divided by a naught. So means this relation is exactly same. Here the point is the best thing about it is you don't have to calculate exactly the number of carbon 14 atom. Instead of going for calculation of carbon 14 atom, we can go directly with the activity of the sample, and it's easier to calculate the activity of the sample. So now by using this is equivalent to that, we can get the A's in terms of even activity, and this comes out to be ln2 multiplied by ln, this is what, an divided by a naught. So it's same thing actually, it's just easier to do the calculation in terms of activity. So this formula you can use if it is provided the number of elements of carbon 14 present in the new and old sample, and if you are not provided with the actual number of elements you are given in the question, it's activity in the present sample and the old sample, then you can use this relation and both are exactly same. So you will get A's in either way. So let's see next problem. Okay, let's see one application of carbon dating. So here we have a problem. Let me read it first. A 50-gram sample of carbon from the bone of some skeleton found to have carbon 14 decaying rate dpm. So means activity in the old sample is 200 dpm disintegration per minute. So here you can see it's not given actually things in terms of the number of carbon 14 elements or atoms present, it's given things in terms of activity. And it is known carbon from the living organism has a decay rate of, so activity in the new sample it's 750 dpm, right, disintegration per minute. T half is also given and you are asked to find the A's of the sample. We can use directly here relation. So T is equal to what? T half divided by ln2 multiplied by ln A new divided by A old. Right? We can substitute the values here. So it's 5730 divided by ln2 multiplied by ln 750 divided by 200. Solving it, we are getting T is equal to 5730 ln 15 by 4 divided by ln 2. This ln natural log you can convert it into log also, and just simplifying it using the calculator you will get T comes out to be 10,000 to like 627 years. So the A's of this sample, you can check the calculation here actually. After solving, just simplifying this, we getting the here it's 10,627 here. So means the age of that skeleton is 10,627 year old. Let me just check the calculation. It's not 6,000, it's 10,927. So after solving this, you will get 10,927. Here also it's 927. So you can see very easily we can find the age with the help of carbon dating, right? So this is about carbon dating. Next point is uranium dating. Let me discuss that point in the next class. Thank you so much.